Thanks, Abib. Thanks for having us here. Let's see if I can try to make up some time because fortunately my good friends Amy, Jason, and Andy already expressed the wish list that I was asked to present today. So I hope to reinforce the needs that they've already articulated. Sticking with while I might have a whole bunch of opinions that pertain to the commercial gaps that we need to fill, I'm going to stick with my homework assignment, focus on discussing a little bit about our perception of what state-of-the-art is in TLP design and what we need to fill technical gaps to get to commercialization. A little bit of background on Glosten as a company. We're a consulting firm of 95 naval architects, marine engineers, and ocean engineers. And while our name is synonymous with the TLP and the offshore wind industry, we actually do a lot of work in, most of our work is primarily in ship design. But we also have a good deal of experience in other offshore structures, particularly semi-subs, and we do a lot of analysis of catenary mooring systems. So our perspective is broader than just the TLP, and it was the perspective that was brought to bear to determine that was what we thought to be the ideal solution for the lowest cost of energy in offshore wind. But our knowledge base goes beyond that, and we've been developing a TLP concept now since in earnest, really, since about 2009, and decided to commercialize it in 2011. And talk a little bit about some of our demonstration project experience because it feeds into the history that I'll talk more about. As many of you know, we were sponsored by the Energy Technologies Institute to develop a feed design for a full-scale 6 megawatt demonstrator for deployment in the Celtic Sea at a test site called Wave Hub. I was hoping that any presentation I'd be giving in October 2015 would be about the glorious success of the installation of that demonstrator, but that has not been the case. That project did not go forward because the Energy Technologies Institute ended up deciding that they needed to reorganize and couldn't continue to invest in projects going past 2017. So we continue to try to develop a full-scale demonstration project. Obviously, that's an important milestone to commercial development, and our primary target right now is trying to make something work in Scotland. But the point is that despite the fact that we didn't make it to demonstration with ETI, they did enable us to do an incredible amount of design, development, and technology work on the PelaStar system and allowed us to surpass several development milestones we may not otherwise have. And so primarily the fact that we were able to develop a 6 megawatt full-scale design, not in exactly the ideal operating conditions for a commercial utility scale platform, and one with a little bit harsher conditions due to a shallow water depth. We had to solve many challenges, but we developed the design to a highly detailed level. We worked with DNV to go through the certification process, got a fully certified basis of design for the platform, and made it about 30% of the way through full design review as well. That gave us a very mature design, one that basically was already in a shipyard's hands to begin fabrication detailing. We were pretty far down that path and had to solve a lot of the practical problems that come up when you do the detailed design of the secondary system support systems for the turbine, access systems, safety systems, the systems that support the installation process. So we're very comfortable with the level of detail of this design, consider ourselves demonstration ready for when we have that next opportunity. I should say that one of the other the key advances that we made during this the ETI design was that we went from what you would have seen in our initial pictures of PelaStar as a 3-arm platform up to a 5-arm platform, which we did because we felt it was important at the demonstration level to increase the robustness of the design. And we get asked all the time, why the 5-arm instead of the 3-arm, and it simply comes down to there are a good deal number of stability issues with a 3-arm design, and we could have built the reliability into a 3-arm design that we wanted for demonstration, but it would have ended up essentially being more than a 5-arm design. So we've found that the robustness that the 5-arm design offers us is a lower cost solution. Perhaps over time we'll find that we don't need that robustness at commercialization, and we can look to maybe drop in a couple of arms, but right now this is what we feel comfortable with. And through the ETI study, we found even with this design, we can aim and expect to succeed at hitting that target of 10 cents per kilowatt hour. And happily, actually, I can say, just 2 days ago, we were awarded the U.S. design patent for the 5-arm design, and had already gotten it in Japan. So that was a lot of the outcome of what the ETI helped make happen for us. So other aspects of the state-of-the-art of this design, we are working with our partners at Alstom and NREL to help develop advanced controls well suited to the PelaStar design. Near and dear to my heart, one of our favorite efforts is the development of the technology that goes into our particular tendon system. We use a parallel wound synthetic fiber cable that is special purpose for this application. It gives us the ability to install tendons in a simultaneous process with the installation of the platform so that we reduce the overall installation time and time at sea. They also provide nice damping properties to improve dynamic performance of the overall system. This is a formal technology qualification process that we've executed with DSM Dyneema and DNV, and we've reached a couple of major testing milestones this year, finishing several 100,000 cycle endurance tests, moving up to an 1 million cycle endurance test soon, and optimizing some of the termination design to improve overall endurance, shooting for a 50-year life on these tendons. Another area that we spend a good deal of our time working on is in simulation and coupled analysis, which we've talked a lot about today, so I don't want to go into too much detail, but today the state-of-the-art for us is in using OrcaFlex to model our system, primarily for the extreme loads that tend to design the structure, and for operating conditions. Unlike our friends at Principal Power, were not able to use what we colloquially call here, I think, OrcaFast, which is OrcaFlex coupled to fast. That isn't a solution that works for the structure with the dynamic properties of ours. So for dynamic modeling, we're using fast coupled with hydrodyne right now, and as I'll discuss more, we're looking to improve on the fidelity of that solution. So yeah, moving quickly ahead to some of the technology gaps that we'd really love to see filled. As I said, many people here have elaborated on some of these, but starting from the category of what we need to improve designs, as we've already here discussed, the improvement in the reliability of coupled and analysis software is something important to us. And I think I would like to bring just to this topic that we do look at this from two different perspectives. And one is, what is the right software platform for innovation? That's what I think we've talked mostly about here, which is maybe a different question than what is the right software platform for design and certification, because those are really serving two different purposes. In the innovation stages, you tend to need something that runs faster, is a little bit more customizable and modifiable. But when we get to the design stage, the key is that we need to extract an incredible amount of information, and we need an extremely high fidelity model to produce all the data that we need to move on to things like detailed finite element analysis and to satisfy the needs of the certification bodies. I do have a vision that one day we could have one piece of software that suits both roles. Today we do not. The other thing I want to bring to the table here is that, in an ideal world, as a developer, I would love to actually create a slide similar to the one that Albert presented today with the platform technologies of all the different software that's out there, because I think it looks very similar. And that's a really difficult world for the designer to live in. We crave as few software platforms out there as possible that are well vetted by industry, so that when we select a piece of software to go to certification with, we don't have to revalidate for the classification or the certification body. That's just a huge effort to convince them that the software that we're using is legitimate before we move on with actually analyzing the design. So we would really like an outcome to be, I know it's not going to be one, but 2, 3, maybe 4 pieces of software out there that are widely accepted by the industry, that have a broad set of capabilities. Some may be better for some applications than others, but we don't want to have to mess through 20 or 30 different pieces of software and revalidation every time we go through the design process. Just to add on to some of the things that Andy pointed out, we do see small-scale model testing as an important step in the validation process. In particular, no matter what we do, I think for some time we'll need the data from those model tests to calibrate our analytical models. And we would like to see active control of turbines be a realistic objective to achieve in the model basin. And one of the biggest downsides for us right now is the problem we have with the weight of the scaled turbines. And as Andy said, I think this is just an engineering problem, not really a huge technology gap to overcome. But to get the dynamics of our system right, we really need the correct scaled weight of that turbine. So we'd love to see the model basins produce the technology that gets us model turbines that match our scale. Another pretty significant design issue for us that we're finding is more and more important as we look at the areas of the seabed that might be commercialized. I think we had a vision a while ago that most of the commercializable sites that we'd be looking at in deep water were going to be in areas of clay and sand and gravel that were going to be ideal to put TLP anchors in with driven piles. And that is still probably the primary anchoring system that we'll use, but the more we see of viable commercial sites and demonstration sites, the more we're seeing rock bed, seabed that we're going to have to put in what I call rock anchors, but are essentially of the configuration of a grouted pile. And there is a relatively small amount of experience base and data out there for these types of piles under the kinds of loads that we're applying in a high vertical upload condition with lots of dynamics. So we are hoping to see a lot of development in this area, and I can also observe that some of the other platforms that are using taut line mooring systems, they're going to start to experience some of the same issues. So I think this is not just a TLP specific issue, this is an industry issue that we need to come up with better, more affordable and more understood solutions for anchoring in rock, particularly when when we need to provide high vertical upload capacity. On a similar note, some of the other technical areas that are really important for future commercialization is bringing down the cost of the work we need to do on the seabed, and that includes both survey and installation of anchors. We need to gather some pretty detailed geotechnical information to get through the certification of the foundation systems. There's some interesting technologies out there in using acoustics to get geotechnical data rather than through coring. We've tried to promote some of those projects and look forward to someday seeing some of that move forward. But I think the absolute most important thing we would like to see happen is the development of subsea drilling technology. We are going to have to be drilling and grouting in anchors, and doing that from a surface vessel will be cost prohibitive at utility scale. This can be done on the seabed with remote drilling devices, and unfortunately the companies who are most likely to do this type of installation hasn't yet seen the demand to make the investment in developing those systems, and that's something that I think that would benefit the whole industry moving forward. And we need that both for installing anchors and for those cases where we need to do geotechnical coring. Lastly, real quick, this might actually even already be overcome by events, but there's still several electrical infrastructure issues that could benefit the entire industry as well, and I've just listed two, which are developing the reliability and the dynamic cables for floating wind turbines and dealing with that motion. I think the cable manufacturers are actually stepping forward with a lot of confidence that they can produce designs that have the reliability that we're looking for. I'm not seeing the same level of confidence in the certification body world, and I think there's still some proving ground to be made up for here, so that we can rely on these cables. And lastly, I think it would be a benefit to have wet mate connectors for 33 and 66 kV cables. Again, I think that's going to simplify, has the potential to simplify the installation process for just about any platform as well. And I'll say that I'm focusing here on issues that I think are really common to the industry, not necessarily specific to one platform type. I think these are things that we're, as a company, certainly see as solving these problems will raise the entire industry, and we look forward to collaborating to help get them solved. Thanks. I would say that in particular for us, they're very similar to what has to be carried out for fixed bottom technology. Now, obviously, it's strongly dependent on how homogeneous the site is. But if you're looking at a driven pile situation, I think there is some limited amount of, there's certainly a whole bunch of magnetometer work that can be done that gives you a lot of information. I think you can do some limited coring, vibrocore samples. It will develop a lot of information. You may need to do a couple of deep cores just to confirm, but driven piles are fairly flexible in their design. You can design a lot of conservatism in them without a lot of expense. If we are in a rock seabed, that story gets a little bit more complicated. It remains to be seen the exact number of cores that we'll need to take. For instance, at the demonstration project level, we were planning to do 3 cores to represent 5 anchors, and these were going to be like 30-meter cores at a 6-inch diameter, and then a bunch of downhole in situ testing of the cored out area. That's not something that we would expect to have to do, for every turbine in a wind park. At a minimum, we'd like, to hopefully find an area. At least seabed rock tends to be somewhat homogeneous on the scale of a wind farm, so that maybe you could do limited sampling. But that definitely needs to be done. And as I said, there are some acoustic methods out there being developed that may provide access to the same engineering data without actually having to core, and that could be game-changing. So for a 6 megawatt unit utility scale economic, we'd like to be in at least 65 meters of water at the low tide level. But we were designing this demonstrator for 55 meters.
It makes a really big difference.
Yeah, it's that there's a big gradient of cost in that depth range. And then when you get beyond 65, you actually get pretty optimum in the 70 to 80 meter range, and then you slightly marginally get a little bit more expensive as you go deeper, just because you're buying more tendon material. But your dynamics still stay inherently good as you go deeper.
Thank you.
All right, thanks.